Okay, good afternoon. We start the flavor session, and we start with this first speaker. That is Dr. Philip Urquijo from Bell 2.
Okay, so firstly, thank you to the local organizers for inviting me to give a talk on CKM and CP violation in the quark sector. I'm here on behalf of the Bell 2 collaboration, but I'm showing results from Babar, Bell, and Bell 2, BESS 3, LHCb, and Chloe. So because this is a session on flavor, I want to remind you of the major motivations for the field. Of course, we're looking for solutions to the matter-antimatter asymmetry puzzle. So new sources of CP violation are motivated from this. Quark and lepton flavor and mass hierarchies suggest that maybe there's particles that couple slightly differently to each of the generations, and it may show up more strongly in the third generation. This gives rise, for example, to things like the charged Higgs W prime and Z prime. You might have something so beautiful as a restored left-right symmetry. One of these might be right-handed. Then there's finite neutrino masses, and finite neutrino masses may give rise to lepton flavor violation, lepton flavor universality violation through the mass generation mechanism. And of course, leptoquarks are an interesting manifestation of grand unification theories that try to put together all of the parameters of the flavor sector. So I've got two symbols here. I've rated a lot of the topics in here either as spicy at the kimchi level or hot at the gochujang level. And this one is definitely a hot area. So we've been probing, in particular, topics of lepton universality through leptonic and semi-leptonic decays through a number of different experiments. Normally, we use these to extract the CKM matrix element magnitudes, but of course, some interesting things have shown up recently. Then we've got two kinds of studies of CP violation, both direct and indirect through interference of decay and mixing. And from this, you can extract the standard model weak CP phases, but you can also search for new CP phases. The search for new CP phases requires that you actually understand, or you can pin down what the standard model would be. And of course, there's a lot of interest in the field concerning lepton flavor universality violation. It's shown up in popular science. And of course, everyone's waiting for Bell 2 to provide its input on it. So just to remind you of some of the basics of the CKM and CP violation, you can essentially, the standard model describes the mixing of quarks of different generations through the weak force. And the CP phase shows up most strongly in the VUB and VTD terms, two terms that you access through B physics. It boils down to having, from the three generations, one CP phase, which is a single source of CP violation in the standard model quark sector. And you can, through unitarity relations, form the unitarity triangle, the area of which is proportional to the amount of CP violation. And we can have many over-constraining measurements of the matrix element magnitudes as well as the CP phases directly. So how do we measure the CKM matrix elements and their phases? I'll start on the right-hand side here. Through a series of semi-leptonic decays, you can access most of these. It's a little trickier in the case of tops, which you can access through mixing. And you can look at them both through semi-leptonic and purely leptonic annihilation processes. You do need to take into account theoretical input. On the other hand, you've got measurements of the phases. The phases denoted, in this case, alpha, beta, and gamma. These are extracted from hadronic decays, both from time-dependent and direct CP violation processes. And there's a large set of flavor data from a whole bunch of experiments around the world. And a lot of them were contributing in 2018 to new results. So Babar, Bell, Bell 2, BESS 3, Chloe 2 has just come online, or just collected their data sets. Atlas and CMS are collecting massive data sets contributing to select topics, and LHCb has contributed in a very substantial way in this conference. So I want to point out that there are a few specialist machines. BESS 3, of course, is a charm factory where they operate to produce charm on resonance or at threshold, and Chloe 2, which is a phi factory, so it's good for studying kaons. The most important big thing for the field, though, is that Super KKB, which has just come online, is the first new collider since the LHC. So firstly, I'm going to talk about leptonic and semi-leptonic decays. There are three ways to measure these. You can go through leptonic and you take a decay constant from lattice QCD. That's this FB. You can do exclusive semi-leptonic You take a form factor parameterization and you normalize, you match that to a prediction of lattice QCD at zero recoil, and you can access your CCAM matrix element. In this case, you have different polarization amplitudes, and an additional one if you've got a heavy lepton, so if you've got a tau in the final state, so you have this additional term. Then finally, if you can measure the full rate of a process, then you can use heavy quark symmetry, and you take out an inclusive determination, and you've got one here. This works very well if you can measure the whole rate. So the first thing I want to talk about, of course, is the anomaly, and this is Gochujang level. This is a large anomaly first seen by Bell back in 2007. And now there's numerous measurements, and the question is really, do we understand our background? So if you look at these processes, the signal in red here, signal in red and signal in red. It's interesting the experiments use the same color. But they're not highly pure analyses, and we rely very strongly on our understanding of different processes that form the background. So the most recent measurements were analyzing various different topologies, one in beta J psi, or B sub C to J psi, one hadronic tau, and another hadronic tau from Bell. We're still to get the final results on the full data sets from the B factories. So the world average is near 3.9 sigma from the standard model expectation. That's the red average here. There are two things to note. RD star with hadronic modes are actually 1 sigma consistent with the standard model. Bell RD star combination is less than 2 sigma from the standard model, so it's not really an anomaly in its own. And when you're measuring taus, they're easily mimicked by background. So one of the measurements that was shown here at the conference is how to measure this problematic background that can peak just like the signal. Another interesting measurement concerning VCB, or at least beta C transitions, was a measurement of D star L nu. And there's been this persistent problem in the inclusive and exclusive determinations of VCB and VUB, here from HFLAB this year. There's your VCB exclusive, there it is inclusive, VUB exclusive and inclusive. So a new result was shown that showed that the way that we analyze it, the way that we form our form factors was probably insufficient up until now. And so we've got this precise new result, which is right in line with the inclusive. So VUB and VUB on VCB have been important recent measurements, mostly published last year. And here there's still a difference of 20%. This was a recent measurement by Babar showing that doing an endpoint analysis, which is where you have only BTU, the modeling is just not working quite right, and we think it's due to this beta C. So we think we'll be able to solve this problem. Another thing was that LHCb is now measuring form factors, and that's very important for their studies of VUB over VCB, but also other studies maybe if they want to study tau. And the biggest result probably this year has been the search for beta mu nu, which is consistent with the standard model expectation. This is a very rare process. On VCD, which is the Cabibbo angle, we have a lot of new results coming from BESS3, and they're really reducing the uncertainties on both semi-leptonic and purely leptonic decays. So on their purely leptonic D to tau nu, there's no signs of new physics. It's precisely in line with expectation. Same with D to mu nu. In fact, you can compare the expectation from lattice and their measurement for the decay constants, and they're basically within 2 sigma of each other. BCS also had new results from BESS. They're doing a lot of work on leptonic and semi-leptonic. This is their latest results, which are the most precise determinations of VCS direct, and they're absolutely in line with the CKM fitter expectation. And once again, lattice QCD has been shown to be able to predict decay constants extremely precisely. It gives us a lot of confidence when we look at leptonic decays in the B sector. So moving on to CP violation, this is a classic way of measuring the phase of the phase of CP violation in the standard model. You look at the time-dependent approach where you look at the interference between a decay to a CP eigenstate and the one where it goes through the mixing process, and we look at the asymmetry over time. We do this via tagging 1B and then measuring its flavor and its decay point and measuring the distance that it flies. Different experiments have very different properties. LHCb has a low tagging efficiency but an extremely high B production rate. There are other requirements too. You need very good IP resolution. You need hermetic coverage very often in order to catch particles like K-shorts. You need good hadron identification. which means good separation between particle species. You're doing flavor. And these are the most recent results. The most recent input has come from LHCb in 2017. So the average now has come down to 0.7 plus minus 0.02. So this is taken from beta J psi K short. We have the interference between mixing and the decay. This agrees pretty well with the indirect determination from CK and Fitter. This tension mostly comes from the choice of VUB. Now, this is what the picture looks like currently, and there's a lot to really improve in our understanding of the CKM. All right, so one of the big questions left was, what's the sign actually on cos 2 phi 1? There's actually a twofold ambiguity. I'll come back to it. This solution and that solution. And up until this year, we didn't have the right answer. So a joint Bell-Babar study shown at the conference showed a 7 sigma evidence for it being positive. So the ambiguity is solved. This is a very important study that was looking into pinning down the theoretical uncertainty in the measurement of phi 1. So I think this is so important, I gave it a kimchi. Direct CP violation is another way that you can search for and measure the weak phase. So what I've shown before is a flavor change of 2, which is mixing and decay, but you can also look in just simply mixing, just decay. Now the trick here is that you need, when you apply the CP operator, an interference between processes with different strong phases and not just different weak phases. If you want to then pull out the weak phase, you need to measure the strong phase, and that's really a challenge. So in the case of phi 3, you do need to be able to measure that strong phase. We take that information very often through Clio or BESS 3 for charm factories, and the relative strength of VUB and color suppression that enters into processes. You saw this already in the plenary yesterday. So phi 3, what's great about phi 3 is that theoretically it's pristine, so it's an extremely precise way of measuring the CP phase. It's also experimentally statistics limited, not systematics. So LHCb combined several channels, charged, neutral, and B sub S. And you see that there's a bit of tension with the indirect determination, which comes from other constraints. There's also self-tension here. This is from B sub S. Now, this is interesting because this is from time-dependent measurements of B sub S, which is fundamentally a different process to the one where you extract it from decay. I should remark that it was always a dream of Bell and Babar to be able to do this, but due to VUB and color suppression, it's quite suppressed and difficult. However, a lot of these approaches were developed there and then adapted at LHCb. Phi 2 is the remaining angle, and you can measure aspects of phi 2 through charmless decays, in particular pi pi and rho rho. LHCb has also extended this to measurements of k pi, which was actually the original source, the original direct CP violation signature of the B factories, and their data is extremely clean and really impressive. So putting it all together, you can get a measurement of phi 2 from all of the inputs coming from B factories in particular. And here you can see the CKM Fitter indirect versus the direct input. You see it's down to 4 to 5 degrees. That's very impressive, and it's in agreement. There are other ways to search for CP violation, where you can have extremely large CP asymmetries, and these are in localized Darlot space. Essentially, you have a certain type of strong phase that enhances the amount of CP violation that you see. So what the experiments had to do is switch gear to do amplitude analyses to actually measure that strong phase. And this is what was shown at the conference. I gave that a kimchi. That one's really impressive. This is another area of very large local CP asymmetry. And you can also study triple products in four-body decays. And this is also another way of probing different weak phases, strong phases. Charm is a field, unlike B, where non-zero CPV would be an absolute smoking gun. We're not expecting to see it. One of the most recent aspects to the study, though, has been continuation into studies of neutrals. So just like in Bs, if you can measure neutrals, you can control strong phase effects that may enhance the standard model signature. So both LHCb and Bell produced new results here, all consistent with zero. There's also been interesting time-dependent or mixing measurements that allow for CP violation parameters that are dead on zero. Finally, on CP violation, I want to move to the Chloe and Chloe 2 experiments. So there was the final Chloe 2 dataset collected on March 30 in 2018. And we're awaiting their CPV and CKM analyses. You can see they collected data for 4 years and just switched off this year. One quite interesting is direct T and CPT tests using quantum mechanical entanglement. And what they've most recently submitted to the archive in the past month was a study of the semileptonic asymmetry, AS, they precisely measured and submitted. And this was used in a study of CPT violation, where, again, the expectation for this particular ratio, also taking input on the K-long asymmetry, should be consistent with 1, and it was. So let me summarize the CKM measurements. The VCB inclusive-exclusive puzzle was addressed, and it was addressed here at the conference. The anomaly beta D star tau nu, as shown here, needs new background studies. We need to understand our background a lot more and more understanding of our form factors. On VUB, on VCB, LHCb has done just that. They've improved their form factors. The VUB inclusive-exclusive puzzle is still a puzzle. It's a different problem to up here, and we're waiting for the final data sets. And BEST3 has delivered a whole bunch of new direct constraints on VCD and VCS that are world best and also outstanding tests of lattice QCD. We can then have a lot of confidence in applying it in other places. As for CP violation, the biggest jump here has been on Phi3, which has improved down to the 4 to 5 degree level. And all these measurements are statistics limited and theoretically clean, experimentally, systematically clean. So with more data, we can only get better. Now, what I'm showing over here is just how much CP violation, what kind of amplitude for CP violating effects we can still have. So this is the mixing Hamiltonian. So you can have an additional CP violating component in the off-diagonal terms, where you have an amplitude and a phase. So for any phase, the amplitude could be as much as 20 or 30%. When we take the data from LHCb upgrade and BEL2, we can push this down to well below 10%. So there's a lot of room for new physics still. All right, so finally, I want to move on to the most exciting part of what's happened in the past year, and that is BEL2 and Super KKB came online. Oops. So the nanobeam scheme was shown in action. The luminosity hit 5.5 by 10 to the 33 this week, and more than half an inverse femtobarn of commissioning data was collected. And we've shown a whole bunch of first studies at the conference. This is one of the first hadronic events shown. Yep. So as for BEL2 and Super KKB, there are more than 800 collaborators from 110 institutions in 25 countries. I want to point out BEL2 Korea, there's 45 members. They make contributions to the calorimeter, trigger, DAQ, and computing for the experiment. And the foreign co-spokesperson of BEL is Yongjun Kwon, one of the local organizers. What I'm showing in this plot here is the integrated luminosity with time that we're expecting, and a very important point for us, which will be a milestone, an order of magnitude jump where we're expecting to really test flavor anomalies. Over here, we've got a plot which is the R2 or sphericity variable that shows that we're collecting Bs. This is the B peak in the signature, and collecting it with about 99% efficiency. This is the summary of the upgrade. Now, it was mentioned yesterday, so I won't go into it in too much detail, just a couple of nice pictures of one of the B events, one of the K shorts that was reconstructed. You can see the full event display here with a displaced vertex out in the drift chamber. And for 2019 operation, we're going to be installing the silicon vertex detectors. This was missing from the commissioning run. Layers 1 and 3 through to 6 will be installed. So most of the detector, certainly we can do our full physics program as of next year. What have we seen so far? We've seen actually tremendous, I think really impressive performance after some initial calibration. Now, commenting firstly on the silicon vertex detector. In principle, it has a factor 2 times better resolution than what we had on the impact parameters in Bell, and a much bigger acceptance for K-shorts, very important for CP violation. And the plot here shows that actually we used this vertex detector to measure the Z profile of the beam, and it proved that, in fact, the nanobeam scheme was working. Here we've got a plot of a K-short signal, and here what we saw was that after minimal calibration, we agree within 5% of our Monte Carlo, and similarly for pi 0 to gamma gamma, we see a very good resolution straight out. In fact, these were about as good as we got in Bell. Particle ID, we've got some new detectors in there. In particular, we've got the time of propagation Cherenkov detector. Here, these plots show essentially where a track has hit a prism bar with a certain momentum, and the light signature that comes through in x versus time. And what we have in the solid lines is the PDF, the expectation for different particle species. And we know it's a kaon because it's tagged. This does not agree with the PDF that we had for a pion, and it agrees very well for the kaon case. So it's working effectively. Also, our CDC DDX, this is a plot taken out of the data, and you can clearly see the bands from different species. With that data set, we're able to rediscover all the charm and charmonium that one would expect to see. But we also found some difficult to see ones, like D0 to K short pi 0. I think this is pretty hot because this is something that's very difficult, particularly in an LHC environment with K shorts and pi 0s. That kind of topology is going to be something we'll use for studies of CP violation. We also rediscovered beauty, shown yesterday. What we were doing is trying to recreate Clio in Argus. This is a famous discovery paper, where we had about 100 B candidates hadronically and about 14 in D star E nu. You can see that nice peak. As for Bell 2 prospects, on CKM, we'd like to push VUB down to below or around about 1%. With excellent detection universality for electrons and muons, so we'll be testing that in the future. And all of our angles we're pushing down either to below 1% or 1 degree. This plot here shows the RD versus RD star projection for 50 inverse autobahns. If there is new physics, we will very clearly see it. These analyses are highly statistics limited. And we're also going after new sources of CP violation, such as in beta eta prime K short. All right, so in conclusion, we've got many new constraining CKM and CP measurements that were shown at the conference in this year. The most powerful tests of the measurements of the CKM matrix elements and the phases are all statistics limited and theoretically clean. One note, LFUV in leptonic and semi-leptonic decays is theoretically clean, but not experimentally clean. We don't have universality of response. So they do take time to understand. And with more data, we'll be able to really probe this. And we've had a pretty big commissioning year. I've got a couple of highlight plots that came from the book. But just to finish, here's a Bell 2 wish list or roadmap of discovery, and a picture of the Bell 2 members who joined at the conference. And I want to point out one of the members discovered the XYZ states with Bell and was the recipient of the 2017 Ho-Am Science Prize. Okay, that's all.
Thank you. I have a question, Phil. When do you think that there will be the new VUB analysis done and solving the puzzle?
Okay, so I'll come back to this summary. There is a VUB inclusive is 20% higher than exclusive, and it's kind of creating a bit of a mess in our precision studies of the unitarity triangle. Inclusive is a rather difficult analysis, and there's still a lot of data to pull out from the Bell experiment. And so in the next year, we're expecting to get a new result.
Thank you. So since there are no other questions, we thanks again the speaker. Neil Stanning, and he speaks about the rare BD and kaon decay.
Good afternoon. It's an honor and a pleasure for me to be here to talk, to tell you about rare decays in beauty, charm, and strange decays. Let me start with the history track record of rare decays, namely the rare decay of a neutral kaon to two muons, which had a very small branching ratio, and then was explained by introducing a new particle, namely the charm quark, and then was later by Professor Lee, where the mass was estimated to be slightly below 5 GeV, before the actual J psi was discovered. And in fact, there's a long list of examples where particles were seen in an indirect way before they were actually discovered in a direct way. And of course, it has to be said that the direct discovery should not be underestimated, the value of those, also indicated by the Nobel Prizes they collected. And not only with these indirect measurements you can find the existence of new particles, but these new particles actually can be very, very heavy. So with precision measurements of rare decays, you can be sensitive to mass scales up to many dozens of TeV. Of course, depending on how strong they actually couple to the standard model particles. So in this talk, I will basically talk about two types of decays. On the one hand, we have decays with a fully leptonic final state, like with two muons or electrons or taus in the final state. And then if you would pull this incoming quark line to the other side, you basically get the decay here below, where now the quark line is in the final state, but it's basically the same diagram. Okay, these are the so-called flavor-changing neutral current electroweak penguin diagrams. Now there's of course also the so-called box-type diagram which contributes, but in the remaining of the talk I will mainly show examples where I indicate the so-called penguin diagram, which is called after the first introduction of the word penguin by John Ellis and collaborators in this paper from the 70s, where you see the resemblance of the penguin diagram to an actual penguin. Now these penguin diagrams are obviously suppressed in the standard model. So these loop diagrams are obviously suppressed in the standard model, and therefore new physics contributions can compete with the standard model on a similar level. So this is the list of decays I want to discuss here. It's a long list of decays, all related to these flavor-changing neutral currents, both in the strange, charm, and the beauty sector. And there's a wealth of variables that we can study. So it's first, of course, the branching fraction, also the decay rates, and then also angular distributions. So this is another way to represent the various decays that I will flash to you. So in the strange, charm, and beauty sector, and then both the leptonics, and if you want we wouldn't call it same leptonic, but maybe half leptonic decays over here. And then special interest, of course, are these decays where we take ratios of decays with different leptons in the final state, which are sensitive to this lepton flavor non-universality. Now the references to the various papers that I will show you are listed here, which indicates also the large interest in these decays and the enormous activity in these searches. Now these are the results which are new since 2 years ago, since the last ICHEP edition, and these are the ones, the papers which came out this year, in 2018. And already here, it's kind of a spoiler, but already here you can see that LHCb did not come out with an update of the long-awaited RK result, including run 2 data. So I'm afraid we have to be a little bit more patient here. So to show you the first result, it's what NA62 showed this year is for the 2016 data, they found one event indicated here of the rare decay of a charged kaon and a pion and 2 neutrinos in the final state. And so they expected about 0.3 signal events and about half of that background, and they quote an upper limit on the branching ratio of about 1 × 10⁻⁹. Okay, and then in the run, which ends this year, they expect to collect approximately 20 events according to standard model predictions. Now, if you change this spectator quark from an up quark to a d quark, then we get the neutral kaon decay to a pi 0 and to neutrinos. And Koto showed a search, and they opened the box for this conference, and they did not see any signal event in their signal region, where they expected about 0.4 background events. So they quote an upper limit of 3 times 10 to the minus 9, where with the full data set, they can put more stringent limits on this decay. So also LHCb joined the area of strange rare decays recently. It's a relatively new field in LHCb. And let me show you 2 examples. One is the search of the kaon decaying to 2 muons. And here around the kaon mass, no peak is seen, so an upper limit is set to 1 times 10 to the minus 9. And where the largest background is the k short going to 2 pions. And if you would misidentify the pions as muons, then this forms obviously a background. But this plot shows that if you would miss the mass hypothesis, the peaks are still well separated. Another example is here a baryonic strange decay of a sigma plus going to a proton and 2 muons. And here we see a nice peak at around the sigma plus invariant mass. So a branching ratio of 2 times 10 to the minus 8 has been quoted. And of particular interest is if you now look at the dimuant invariant mass of these decays, because the HyperCP collaboration in 2005 published the same decay, and all 3 events that they saw, the dimuant invariant mass peaked around 214 MeV, and surprisingly close together. So we also plotted the dimuant invariant mass for our sigma plus decays, but no peaking structure is seen around this hypothetical new scalar particle, and therefore a limit has been set to the branching ratio of a proton and a neutral scalar to 1.4 times 10 to the minus 8. And so this interesting signal could not be confirmed. So then moving to the charm decays, this is obviously interesting because it probes a different type of quarks, namely the up-type quarks, where in this case a B quark or down-type quarks would run around in the loop. And this is an enormous data set in LHCb. Okay? So this plot indicates the data distributions of D zeros and D pluses. So it's over 1 billion decays with actually quite reasonable low backgrounds. And with this we can look for rare decays. And in fact, the rarest charm decay ever has been reported, namely a D0, which decays to a kaon pair and a muon pair with this penguin diagram. So the ones with the pions, so if you would here have a D quark pair, we get the 2 pions in the final state, which are a little bit more abundant than with the kaons. And if you then add also the run 2 data, you can even start looking at asymmetries. And for now, no asymmetries which deviate from 0 have been observed yet. Now, if we now look at the baryonic variant of this decay, where we add this UD diquark in our diagram, then we can inspect the region, the interesting region of this decay, namely the non-resonant region in between the rho and the phi resonance, and look for in the mass region of the lambda c, but no excess has been observed, and indeed an upper limit has been quoted of about 8 times 10 to the minus 8. So these rare charm decays are also looked for by BEST 3, so they show the wealth of results this week. For example, if you here now have a charm quark here as a spectator quark, you can look at the J psi's decaying to a D0, or the psi 2s to a D0 with an electron pair in the final state. Okay, so stringent limits of around 10 to the minus 7, around 10 to the minus 7 has been put here. So similarly, they looked at the D0s decaying to an electron pair and a hadron pair, or in the case of a D plus to a single kaon or pion, and indeed limits around 10 to the minus 5, 10 to the minus 6 have been placed. So a wealth of new results here. So that brings me to the beauty sector. So the first example is the well-known BES to mu decay, which has been an historical endeavor which started all the way back in the 80s, and the limits have been improving and improving while the B data samples have been increasing and increasing until the moment that we actually reached the discovery at the LHC of this particular decay. And just to remind you, this is sometimes called the golden channel for SUSY, because if you have new scalars and new Higgs contributing to your decay, then your branching ratio can substantially get increased. So Atlas of CMS and LHCb jointly showed the discovery of this decay in 2015, and also with a substantial peak of B0s actually, which has been updated recently. Now this is not a very easy analysis, because the signal, the branching ratio is really small, below 10 to the minus 8, while the backgrounds are coming from semi-electronic decays with 10 million times larger branching ratios. Now we use data-driven methods to control our analysis. For example, the B2 pi plus pi minus have a very similar topology, so we can actually calibrate our selections. And also JPSI and epsilons we can use to calibrate the width and the mass resolution around the BS region. So we updated this result last year in 2017, and LHCb quote the 7.8 sigma significance for this BS to mu decay. And now the B0 actually reduced a little bit. So it's just a warning that sometimes 3 sigma evidences of these measurements can actually disappear. Yeah? So for the B0 now, this has been reduced to an upper limit of 3.4 times 10 to the minus 10. So if you look at these, the change of these results in a two-dimensional plot of the B0 branching ratio as a function of the B sub S branching ratio, and where you also see the Atlas measurement here, which shows a little bit less signal than CMS and LHCb, you can also see here that the B0 branching ratio actually reduced here from 4 times 10 to the minus 10 to about the most likely value of between 1 and 2 times 10 to the minus 10. And so instead of more than 3 sigma, the B0 signal is now about 1.6 sigma. Not above the standard model prediction, by the way. This is a mistake, sorry. Above 0. So given these B sub S decays, we can try to add a second observable, which is the lifetime of the B sub S. So if there would be new particles, for example, scalar contributions that add to this decay, then the CP structure of the decay can change, and the number, the ratio of the B sub B heavy and the B lights in your decay can change. And as an effect, the lifetime will be affected of this particular B sub S to mu decay. And the first attempt has been done with, of course, limited statistics, but this is something which can add sensitivity to new physics in the future. So we also looked at the B's decaying to tau mesons, and this is of course analogous to B to mu. But this case, the branching ratio that you expect from the standard model is much higher. It's 2 orders of magnitude higher, because the helicity suppression with taus is much less due to the higher mass of the tau leptons. So in this analysis, we used the taus that decay to 3 pions, and we exploited the intermediate rho zeros, and we normalized it to decays of B's to D mesons. Okay, and limits have been set both for the B sub S and the B0 at the level of a few times 10 to the minus 3, which is slightly better, but in the same ballpark as was published by Babar a while ago. Okay, and it's still far away from the standard model expectations, which are in the ballpark of 10 to the minus 7. So we also looked at the lepton flavor violating modes, but this might be discussed in more detail later today. And the limits have been set for the BS to E mu and B0 to E mu in the ballpark of 10 to the minus 9. And similarly for the D0s to E mu, and where we even see a slightly negative fluctuation of around the D0 mass. So let's move to B decays where we also have hadrons in the final state. And so we take this penguin diagram, and we can now add, for example, a D quark as a spectator quark, which lead us to a B2K star mu decays. So now we can not only look at branching ratios or decay rates, but we can also look at angular observables, so the angular distributions of your muons and hadrons in the final state. So this has been an effort which is a joint effort by many experiments. So it's Bell, LHCb, CMS, and Atlas all look at these decays. We see the 4 mass distributions from the 4 experiments. And not only we have different experiments, but we can also look at different hadrons in these particular decays. So you can add an up quark, a D quark, or an S quark, or even di quarks, but we all probe a similar Feynman diagram if you want. Now, and interestingly, if you then look at the decay rate as a function of your di-muon invariant mass, we see that it's always a little bit low, the data, compared to your colored expectation bands. Where it should be said that if you had these bands where the data is missing is around the J psi and psi to S peaks, which is not this diagram. Okay, so this diagram where we look at the non-resonant flavor-changing neutral currents, the most interesting region is here, the low Q-square region, below the J psi peak. So, as I said, we can not only study the decay rate, but we can also look at angular variables. And one of the things that was already flashed yesterday on the screen was the P5 prime. And P5 prime is an asymmetry which I want to illustrate with this chessboard here. It's the asymmetry between the events that fall in the blue region and in the red region. Where the blue region is already a mix of kaons going in various directions in the B mass rest frame. Okay, so it's a mix of forward and upward kaons and backward and downward kaons. And then for the red events, it's the opposite. So if you take an asymmetry of these kind of events, you can already feel that any experimental effect is nicely mixed throughout this phase space. So experimentally, it's a quite solid observable. So this is the P5 prime asymmetry measured as a function of Q square. And this here you see a slight tension with what you expect from the standard model, okay, which is estimated to be a 3.4 sigma effect or so. So now more experiments have looked at this, of course. So it's also Bell and Atlas and CMS. And now the points scatter around a little bit. So for example, you see that here CMS is a little bit lower, and here this point from Atlas is a little bit higher. And LHCb and Bell seem to agree quite well. And which you can also see here from the plot from CMS, which shows that they're a little bit lower. Now, it should be said that it's very interesting that CMS has now a dedicated, or actually has a dedicated trigger, especially designed for this low Q-square region of these K-star mu events. So that's very good that we collect more and more statistics to pin down the experimental uncertainties in this region. It is really dominated by statistics. Now, not only experimentally there's some variation, but if you now look at the theoretical contributions or predictions here, you see that if you would now fit the data and you would allow any freedom for your hadronic effects, then you can actually get this enhanced value of P5 prime in this region. But then the question is this freedom and the resulting hadronic parameters that you get here, is this realistic or not? So there's also a theoretical debate on how to interpret these predictions. So just to show you a little bit why this caused so much excitement, I want to show you a little bit what this implies for the couplings and what this means for any new physics models that people think about. So one famous example of an effective coupling we all know is the Fermi constant, which describes effectively your beta decay, and which we now know can be described by this W propagator. Now, similarly, we describe these flavor-changing neutral currents with effective couplings, and if you would zoom in, we get our penguin diagram there. Now we can quantify this effective coupling in various ways. So we can now separate off the couplings with a vector nature, or maybe an actual coupling nature, or maybe even a vector minus actual coupling. And these are these famous Wilson coefficients C9 and C10. Okay? So now the question is, if we see any effects in these couplings, would this be caused by any change in vector coupling, or maybe an axial coupling, or maybe right-handed couplings? So this is the game that's been played. Now if you do that, interestingly, you see that all these measurements that I just showed, they all point in one direction, namely that only a single extra vector coupling is needed to improve your fits by a large amount. Okay? So if you add a little bit of C9, so a bit of extra vector couplings, then both your branching ratio measurements and your angular information, they all seem to agree with the single simple shift of your C9. Okay, then also the other possibility would be to have a little bit of extra C9 minus C10, which would be a little bit extra V minus A couplings. Okay. So this is why this caused a lot of excitement. Okay, so that all these measurements, so 175 measurements or so, all agree with this single shift. So this justifies a more close look into these flavor changing with the current measurements. And for example, also one of the measurements we did is to compare this non-resonant region around the J psi and what kind of relative phase this has to the non-resonant region. And also CMS just published, or at least it's still preliminary, it's sent to the archive, an angular analysis of the B plus to K plus mu mu. Still in agreement with the standard model. And LHCb recently came out with a measurement of the similar diagram, but now a B to D flavor changing neutral current. And this, of course, suppressed because the VTD is a smaller magnitude than the VTS, and therefore the signal is quite small. But still, with 3.4 sigma, this has been shown. In agreement with what you would expect from suppression of VTD and VTS. So that brings me to the lepton flavor and universality measurements, where we can now look at the ratio of these decays with 2 muons and 2 electrons. And here, all the theoretical uncertainties basically cancel in the ratio. Yeah, so the same form factors and charm loop effect will play a role in the muons or electrons in the final state. So the standard model expectation is pretty close to 1 and with a pretty small uncertainty. And what we measured is something which is about 25% lower than 1. Okay? And you see here also the Babar and Bell results. So then we looked at the analogous decay of neutral kaons, so the B0 to K star mu mu over K star E. And also there we see a smaller ratio, smaller than 1. Yeah? Also again with about a 30% smaller value. Now, experimentally, I should say that this is a quite solid measurement because we take not just the ratio of these K star mu mu over K star E, where theoretical uncertainties cancel, but we actually take a double ratio, where we normalize the muons to K star and a J psi, where the J psi goes to muons, and we do the same on the electron side. So if there would be any funny things happening in your electrons, in principle, it would cancel out in the ratio, and the same for the muons. Now, these measurements are limited by the statistical uncertainty of your electron channel, as is indicated here in these plots below. And you can judge that the statistics is not yet great. So these are the full plots, so the mass distribution for the electrons in the 2 Q-square bins, and this is for the muons, and on the left you see the normalization channels of the K star and the J psi. Where also here you see that for the J psi, K star, J psi to electrons, you see that the tail to the left due to Bremsstrahlung is more affected than in the muon case, and then we can use this shape also to fit our K star E. So many checks have been done to check this result. For example, we look at the absolute ratio of K star J psi mu mu over the K star J psi EE. And of course here the error is a little bit larger because we don't have this double cancellation. Then we checked also this double ratio of the psi to S and the J psi, which is unity within 2%, which is about 1 sigma. And also we checked the K star gamma, where the gamma then converts to an electron-positron pair, and this also agrees pretty well. Now this is one of my favorite measurements. This is a measurement from Bell, because if you now look at this, if there is something that makes a difference between muon and electrons, and if there's something that also affects your angular distribution, then the next step would be to check your angular distribution in the electron mode. And this is exactly what Bell has done. So if you now look at this P5 prime observable, then if you split this between the muon and electron mode, you see that the muons are off and far away from your expectation, whereas the electrons actually are closer to what you expect. So if you would be able to do this measurement with high precision, then I think that's a very strong measurement that can teach us a lot. So, and just to conclude this, we already saw by other speakers, and I think we will see it again, is that also in the same leptonic decays, there seems to be an intriguing difference between the various leptons, about almost 4 sigma difference. It is done by many experiments in different char modes and in different tau final states. So this is a large analysis effort. So just to finish with a short outlook. So as we just heard from the previous speaker, Bell 2 is coming online pretty nicely, and we all look forward to this beautiful machine with a lot of interesting results ahead. And then for LHCb, what we can say, or what we hope to achieve at the end of run 3, that will be around 2024 or so, are these level of uncertainties for the P5 prime observable as a function of Q square, which would then lead to these contours, 3 sigma contours, in this C10 versus C9 plane, which would be able to allow us to save this extra possible new physics if this is as a more vector nature or more a V minus A nature. And if you would then extend it to an upgrade 2, which we are preparing now, then these contours shrink a lot, and this is what we hope to measure in the future. Okay, then my final slide. I think precision measurements, I hope I convince you that this is a very powerful way to scrutinize the standard model, and it's the only way to reach extremely high mass scales of dozens of TeV, possibly. And also most measurements I showed you, I think all of them actually, are statistically limited still, so they're not yet precise enough. Thank you.
Thank you.
I'm asking, have you considered using the blending strategy, in introducing a blending strategy to the flavor physics? Because for this, like 3 sigma discrepancy, you may, for the event selection fitting, we can unblend it, but for the final stage, we compare the mu and the EE, we may try blending, and after analyzing the systematic effect, we can unblend. Have you considered this?
So we certainly also do our analysis blind, and for the update of RK, what I can say is that we will first unblind the run 1 data set to see if that would agree with the published one, and only when we understand that result, we will continue to unblind the additional data set.
Sorry, here. Hey, back here. Niels, I'm over here.
Oh yeah.
Hey. Okay, on your P5 prime, you showed now that we have Atlas, we have CMS, LHCb, and Bell as well. So we've had some combination from the theorists, I guess, on that measurement. But do you know if there's any prospects for combining the experimental results? Have there been discussions between the collaborations, either just at the LHC or also more globally?
I'm not aware of a combination yet, but it's possibly a good idea. But it's not my call. But okay. I think in the end, the communities that make fits to these data, they combine it all. So in the end, the combination is somehow implicit in the fits by the theoretical community. So I don't know what is the added value of combining the experimental data first. But,
okay, thanks.
Could you comment on LHCb prospects on your favorite measurement, that is P5 prime E versus mu?
So when I ask people about the P5 prime with electrons, then people are interested because it's indeed interesting, and I know that people are working on it. But also my colleagues tell me that they find it very difficult. So I don't know when we can expect anything soon. Electrons is not our best probe.
On the issue raised by the previous questioner, is it really a good idea to combine these one-dimensional distributions? It may be better to do the full angular analysis with a theory Monte Carlo in each experiment and extract the Wilson coefficients that way. I think combining 1D projections is not optimal.
Okay, I don't know.
Yes. Go.
Are you suggesting that you think the theorists can understand how the experimental errors, systematic errors, are to be handled better than the experimentalists? When you say that there's no point in the experimentalists combining their results?
Okay, so one thing what might be interesting to combine the experimental results in relation to the theory predictions is that if the highest debated effect would be charm loop effects, which play a largest, which are also vector couplings, which is why people think that that might contribute to the C9. And that would be bigger close to the J psi than far from the J psi. So if you would combine your experimental results and you see a clear trend as a function of Q square, then maybe that give a hint of how whether this would be new physics, it would be more flat in Q square, or whether these would be hadronic QCD effects as a function of Q square. So the Q square dependence is one of the handles that can help there. But again, I don't know if first combining the experimental results and then whether that gives any additional value than just fitting it. That I'm not sure of.
Okay, thank you very much. Oh, sorry.
Sorry.
Yeah, sorry, I missed.
Do you know when the Koto experiment will reach the sensitivity of the standard model or below?
Well, what the authors say is that okay, let me see if I can get a slide back. I think they can improve their limit by a factor 3 or so in the next couple of years. So I think it's not so close to the standard model. Yeah, it's still quite far away with the next couple of years. See, so they expect a limit about 1 times 10 to the minus 9, whereas the standard model expectation is a fraction of 10 to the minus 10.
Okay, so we thank again the speaker. Now we have the next talk on charged lepton flavor from Mihama-sama.
Yeah, I'd like to thank the organizer for giving me a chance to talk on this topic. I slightly simplified my presentation title since it was too long. And yes, very glad to talk about this topic at this largest conference room where I've ever made my presentations. I have 2 apologies. I tried to cover all the topics presented in the parallel sessions, but I may not be able to talk about all the results or topics presented there. This is first apology. And second apology, I took the very spicy noodle for lunch and I finished it, and still something feels hot around here and not be able to speak loud. If you have some difficulty, just let me know. I ask them to increase the volume of the microphone. So let me start with my presentation with this excellent result of the Fermilab G-2 experiment. They actually started the data acquisition this year, and you can see the statistics has already reached the level of the previous Brookhaven experiment. So this is a really surprising achievement of their experiment, and I hope that they will get more data and publish the result in pretty soon. So the outline of my presentation today, I will give a very brief introduction for today's topic, and then they explain the muon child lepton flavor violation experiments, MEG2, COMET mu2E, and the mu3E. Then I try to explain the situation of the muon G-3DM experiments, two experiments. One is the Brookhaven, the Fermilab experiment, as I already showed the statistics. And the second one is the JPAC G-2 EDM measurement. I try to mention a little bit about the tau child lepton flavor violation before summarizing my talk at the end. So let me start. The motivation of searching for the child lepton flavor violation is certainly the new physics effect, as shown in these T-shirts made in the MEG2 collaboration. Yes, Suji was a very strong motivation when we started this experiment. This is because the child lepton flavor violation, that rate is in the standard model, even with non-zero neutrino mass, it's quite small, since this is suppressed with all the ratio of the neutrino mass and the double Boson mass. And it is extremely small, and this is negligible in the experiment. So once we observe any event in the experiment, that will be a clear evidence of the new physics. I try to explain the three decay modes of the muon. First one is the mu gamma decay. The muon goes to the electron and gamma is emitted. And if you add the quark line here, this will be a mu conversion. And if you add the lepton line, then electron line, this will be a mu2 3e decay. And of course, even if we observe the signal, it's not easy to understand what kind of the physics behind this circle. But in case of the mu conversion and mu2 3e decay, some other physics may contribute to this decay mode. So in this case, by measuring all the three decay modes with almost similar sensitivity, we may be able, and comparing those ratios, we may be able to get the information what kind of the physics or what kind of the force are working in this diagram. In case of the mu gamma and the mu2 3e, once we observe the signal, we may be able to use a polarized muon beam and then measure the decay angular distribution of the electron or gamma in the detector system. Then we may be able to get the further information what kind of the force are working inside this circle. As for the G-2, the motivation is almost the same. New physics effect can come in this circle, and this is called the anomalous magnetic moment. And experimentalists try to measure this mu very precisely, and theorists try to measure this, try to calculate extremely precisely with these contribution from the standard model. And if that two numbers are different, then that must be the effect of the new physics effect. And as you probably know, that the Brookhaven measurement already showed the deviation of the standard model prediction larger than the 3 sigma. So let me start the experiment status, MEG and MEG2. MEG is an experiment trying to search for the mu gamma decay at the Paul Scherrer Institute by using the world's most intense DC muon beam provided by the cyclotron at the PSI. And the MEG required, and MEG2 as well, and also mu3E also required a low momentum muon beam to be stopped in the muon stopping target located at the center of the spectrometer. And for doing that, as I said, a high intensity continuous muon beam is necessary because all of these experiments try to measure the multi-particle in the final state. So the accidental overlap will be a severe background in the analysis. In that sense, the DC muon beam, continuous muon beam is really necessary. This describes the setup of the mu gamma MEG detector, and that is composed of the gamma detector, the liquid xenon detector, and the positron spectrometer surrounding the muon stopping target located at the center of the spectrometer. MEG already finished the data acquisition, and the final result was already published. And you can see the number of 4.2 times 10 to the minus 13th. And this is the stringent limit in the child lepton flavor violation area. And I guess this is the smallest number on the particle data book. MEG group is now upgrading the detector, which is called a MEG2. Almost everywhere, detector resolution will be doubled. I mean, the twice better resolution will be achieved by upgrading the detector. As for the gamma ray detector, the photosensor will be replaced from a part of the photosensor is replaced from the photomultiplier to the silicon PM. And tracker is also modified from the multi-layer tracking system to the single volume tracking system. And some additional detectors are installed in order to identify background. And the muon beam also increased compared to the previous MEG experiment, or almost double of the muon intensity will be realized. And by using this modification, MEG2 is trying to reach a sensitivity of 6 times 10 to the minus 14th in 3 years running. Let me move on to the mu conversion experiments. A search experiment. I try to describe the comet and the mu2e at the Fermi. Just briefly, what is a mu conversion search? When the muon is stopped in the material, usually muon forms a negative muon, forms a muonic atom. And usually this muon decays in orbit or captured by the nucleus. In either case, thanks to the neutrinos in the final states, lepton flavor is conserved. In case of the mu conversion, only one electron is emitted in the final state. The electron carries almost all energy of the muon mass. And since there is no neutrinos in the final state, there is an energy of the electron in the final state is almost as large as the muon mass minus the binding energy of the muon and the recoil energy in the system. In case of the aluminum, the energy of the electron is 105 MeV, and this is an important number to identify the signal from the mu conversion. The another important technique to identify the mu conversion is to use the lifetime of the muon inside the muonic atom. Since the muon has a lifetime shorter than the free space, in case of the aluminum, the lifetime is about 860 nanoseconds. And by using this lifetime, we identify this energetic, this electron with a specific energy with a delayed timing. So if the electron is emitted after a few hundred nanoseconds after muon injected to the target, and if that electron has this energy, that is identified as a signal of the mu conversion. So this is the result of the previous experiment carried out at the Porsche Institute Syndrome 2 experiment, achieved the mu conversion upper limit of 7 times 10 to the minus 13th. You can see the long tail of the muon electron energy from the muon decay in orbit. And here is the expected signal, and they were not able to see any signal in this region, so they set the limit of this. In this case, they used the gold as a stopping target, so the signal energy is a little bit different from the aluminum case. But the experimental technique is in principle same, even if you use a different type of the target for stopping the muon. An important parameter to identify the mu conversion signal, as I said, we need to use the timing of the electron emission. For doing that, we need to prepare the precisely pulsed proton beam. An experiment is usually done in this way, in such a way that the proton injected to pion production target, and then the pion decays to muons, and the muons are stopped in the muon stopping target. And after the pion arrives at the muon stopping target, we simply mask the detector, since lots of the background are coming out from that pion stop in the muon stopping target. And after a few hundred nanoseconds, we start the data acquisition. And if we identify the electron signal in this timing window, that will be identified as a mu conversion signal. So important thing in this experiment is that we need to precisely pulse the proton beam. If any leakage of the proton from this pulse to in between the pulses, that can easily produce a background through this process. So the ratio of this number of protons in between pulses to the number of protons in a pulse is called the extinction factor. And in a comet or mu2e, Either case, this extinction factor has to be very small, smaller than the 10 to the minus 10th level to realize the target sensitivity of the experiments. Both experiments requires a large amount of the muons, and this is actually realized by locating the pion production target in the magnetic field with a gradient inside in the gradient magnetic field. And then when the proton hits the pion production target, pions are produced, and that the pions are collected by the magnetic lens effect, which is depicted here. And then that the produced pions will be transported through the curved solenoid, as shown in this picture, to the experiment area. Mu2E case, Mu2E uses a S-shaped curved solenoid to transport the muon produced in this pion production target to the experiment area. In COMET case, we use a C-shaped solenoid magnet to transport the muon to the muon stopping target. And in the COMET case, we use, again, another C-shaped spectrometer magnet to separate the momentum of the signal electron. The status of the COMET experiment. Actually, this COMET experiment tries to reach a sensitivity of 3 times 10 to the minus 17th in 2 steps. In the first step, which is called a phase 1, we construct a detector down to the end of the first end of the 90-degree band and locate the mu-E conversion detector here. And then the muon is stopped at the center of this detector, and the electron is measured by the detector system surrounding the target. In phase 2, the magnet is extended in this way, and the muon stopping target is located here. And the electron is analyzed by this curved solenoid again and identified by the detector system located at the end of the chain of the solenoid magnet. Target sensitivity of the phase 1 and phase 2 are shown here, 10 to the minus 14th in phase 1 and 10 to the minus 16th, better than 10 to the minus 16 in the phase 2. A situation of the COMET experiment is shown here. This is the overview of the JPark. And the COMET experiment will be constructed in this experiment area. This is an overview of the experiment area. And at the moment, we are now preparing the beam transport line from the accelerator to the experiment area, and also arranging the magnet in this experiment area to deliver the beam from here to the COMET experiment hall. And inside the COMET experiment hall, curved solenoid is already installed, and this pion capture solenoid system is now being constructed. A detector is being prepared by the collaborations. We are going to prepare the 2 types of detector. One is for the physics measurement, composed of the CDC and the trigger counters. The other one is the beam measurement detector, composed of the straw tube tracker and LYSO calorimeter. And actually, this beam measurement detector is a prototype of the phase 2 detector. So we are doing constructing the beam measurement detector as well as prototyping of the phase 2 detector as shown in these pictures. Just one slide about the beam, proton beam study. As I said, the beam extinction is quite important to realize the target sensitivity of the experiment. And at the JPark, we carried out the 2 different types of the experiment. One is the fast extraction measurement of the extinction. This is a snapshot of the beam inside the accelerator. And the other one is a real slow extraction measurement of the extinction as shown in here. And at the moment, we already achieved about 6 times 10 to the minus 11th extinction factor, and further development is expected with more study of the accelerators. As for the Mu2E at the Fermilab, they also use 8 GeV proton beam provided from Fermilab accelerator complex. And they plan to use the delivery ring located here for doing the pulsing of the protons. Single event sensitivity is almost same with the COMET experiment, and DAQ is expected to start in 2022, and the 1-year commissioning and the 3-year data acquisitions are expected. Status was presented in the parallel sessions, and the facility construction is ongoing. You can see the many coils. These are used for building that S-shaped curved solenoids, and the detector construction ongoing by the collaborations As you can see here, this is the status of the storage tube tracker to measure the electron momentum, and the calorimeter prototype study is also ongoing. And just one slide to introduce another experiment at the JPAC to search for the mu conversion, which is called the DME experiment. This experiment tried to use a pion production target as a muon stopping target and measure the electron with a delayed timing by using the beamline as a spectrometer. And this was presented by my colleague, Hiroaki Natri, 7th of July. I should a little bit speed up. And the mu3 situation, this is an experiment tried to measure muon decay to 3 electrons. Target sensitivity is 10 to the minus 16 in 2 steps. It is necessary to measure all the electron tracks very precisely. So the tracker is a key component of the experiment. And background source for this search is 3 electron plus 2 neutrinos, or the accidental overlap of the different muon decays. And beamline has to be shared with the mega experiment. Detector preparation is ongoing by the collaborations. The important detector component is the tracker. They successfully tested the first large area prototype, which is called the MuPix 7, MuPix 8, and the MuPix 9 and MuPix 10 will also be constructed before starting the experiment. Timing counter development are also ongoing, and it looks that they already achieved necessary timing resolution for this detector. Muon G-2 and the ADM situation. Since the G factor is different from 2, when the muon is injected in the storage ring, that the muon spin precesses as shown in this picture. The general formula, this is a well-known formula, how the muon spin precesses in the magnetic and electric field. And Brookhaven and the Fermi-Lab approach is to take the magic momentum to erase this term, momentum 3.1 GeV, then this term disappears, and this formula can be simplified in this way, and by measuring this oscillation frequency, they can measure this mu value very precisely. This is the previous experiment conducted at the Brookhaven. I already shown this picture, so that their measurement is certainly deviated from the standard model prediction. Just recently, one interesting paper was published. They analyzed Chloe data more carefully, and they treated the error matrix more carefully, and came to conclusion that the central value didn't change, but they succeeded to the theoretical error, which means that the deviation from the standard model is now 3.7 sigma instead of the 3.6 sigma. So they calculated more carefully, and central value didn't change, but the error was reduced, and thanks to that, they achieved this calculation. This is a famous setup of the Fermi-Lab G-. They brought the muon stretching from Brookhaven to Fermi-Lab. And as I already shown, they succeeded to accumulate the statistics of corresponding amount of the previous Brookhaven experiment. This is the plot shown in the parallel session. They already achieved 1.2 ppm statistics, and analysis is now ongoing, and hopefully the first result will be published pretty soon. Another muon G-2 measurement at the JPAC, it's take a different approach. They plan to do the measurement by using a storage ring with zero electric field. In this case, this formula is simplified in this way, and by measuring the frequency of the muon spin precession, they can evaluate this mu value. And also, if you look at this term, this is a term linear to electric dipole moment. And in this case, muon spin precession direction is up. By measuring the up-down symmetry in the detector system, it's possible to evaluate the muon EDM with the same setup. So this is the approach of the JPAC. And for realizing that the storage link with a zero electric field, they have to prepare ultra-cold muon beam. This is actually realized by stopping the muon beam once in the stopping target, which is made of the aerogel, and then a muonium is formed, and that muonium is ionized by injecting the laser, and then the muons are produced almost at the stop state. And these muons are accelerated by using the linear accelerator and injected to the muon storage ring. R&D of this muonium production by using the aerogel is nicely ongoing. They use the laser ablated holes in order to enhance the muonium emission from this target to the outside. Acceleration tests actually conducted at the JPAC by using the existing RFQ. They accelerated not the muon, but the muonium atom, two electron plus one positive muon, and they succeeded to accelerate the muonium atom by using the setup. And this is a very interesting approach showing that the muonium atom was certainly accelerated by the system. Just one page for the tau lepton child lepton flavor violation searches using the tau lepton. This is summarized by the Bell colleagues, and you can see that this is a situation of the tau lepton flavor violation searches by the experiment listed here. And Bell 2 is now starting, and Bell 2 is expected to push down the upper limit or some discovery of any signal among these many different kind of the tau decay channels. So I guess I reached my concluding slide. Yes. So 3 sigma, larger than 3 sigma deviation from of the muon G-2 in the Brookhaven experiment was existing, and now that will be clarified by the Fermilab G-2 experiment pretty soon. And to check the result, or by using the different method, the JPAC G-2 EDM experiment is now being constructed, and they succeeded to the initial test of the muon acceleration. MEG limit, this is a stringent limit of the 4.2 times 10 to the minus 13, and try to push down 1 order of magnitude by upgrading the detector to MEG 2. I explained the 3 experiments, and these were expected to start sometime in 2019 or 2020X, and hopefully in the coming 5 years, we can see the very interesting result from these experiments. And the more data, tau data, are expected from the Bell 2 experiment. That's it.
Thank you. I have a question for you. When do you think the first results from FNLA will come from Fermilab, from G-2?
Say again, please.
The data analysis for the data that already taken.
Can you say again, please?
So the data from the G-2 that started.
Yes.
The first analysis, the first result.
First result is expected next year, as long as I know. So perhaps the next year, summer conference, we can see the result.
If you had to identify what could be the possible source of experimental systematic in the case of the Fermilab, what used to be Brookhaven Fermilab measurement, what would be your guess, if any, if you have any guess?
No, I don't have anything. Yeah. We need anyway the confirmation by using the same setup. And also, this is actually the motivation of the JPAC G-2 experiment. They try to measure the same number with different setup. So,
but I noticed that they decided not to use the same. I mean, in the one case, the E was set to 0. In the other case, so was there any? Do you understand the motivation for that switch? I mean, that suggested that perhaps there was some thinking about a possible source of systematic.
As long as I understand, they are making effort to reduce the systematic as much as possible by improving the magnetic field measurement, so on. But, sorry, perhaps I don't understand your point. Okay.
Okay. So, if there are no other questions, we thanks again the speaker. And now we go to the talk, the theory talk, to wrap up the session from Svetlana Faufer.
It's a real pleasure for me and an honor to have a chance to talk about flavor theory and outlook. So let me start then. It was very difficult to decide what to put in this very broad subject. And I was thinking what one can do, and I decided to take this hot subject of beam meson anomalies, and I also try to see what's going on with muon anomalous magnetic moment. And the main goal of this is to clarify what is the standard model contribution. And then if we really cannot explain all these phenomena with standard model contributions, that we have to go to new physics explanation. And when we do so in theory, we have tools like effective Lagrangian approach. Then after that, we have to go to models of new physics. When doing this all, we have to look for all possible constraints from all low energy observables as well as from LHC data. And then I will briefly mention what's happening if you go from new physics in B to what is the effect on chaotic physics. I would try to make, to select what are the most important predictions relevant for LHCb, BEL2, and LHC. And the final goal would be to see how far we are from some theory which eventually can be UV complete. And keeping in mind this, what we called flavor puzzle, and you will see later on what's the meaning of this. So first thing, why B anomalies are important. Let me be very pedagogical. And when we teach students about lepton flavor universality, we take this example of this very clean muon decay, and muon decays to electron and these two neutrinos. And due to the same coupling for the muons and electron leptons, one can also get that for tau, you have these relations which holds pretty nicely. What's the origin of this? If you just look, for example, in kinetic part of fermionic Lagrangian, and I'll just put here only the left-handed leptons and quarks, which are doublet of SU2 group. That means it's neutrino, electron, and it's also up quark and down quark for all three generations. Then universality means that this coupling, which comes in the covariant derivative, is the same for all fermions. So that's how we teach that, and that means that really we get it for free lepton flavor universality. Then this famous coupling G enters in the Fermi coupling constant in the effective Lagrangians of the weak interactions where we have these charge currents. That's what we teach on the first year of study our students. Okay, so if we have universality, then one would expect from Dirac equation that muon anomalous magnetic moment, which is this term here, should give G to equal to. And then, since we got quantum electrodynamics, Schwinger pointed out in 1947 that there is an electromagnetic correction of the order alpha of pi. And when you want to get higher precisions, you have to include higher orders in alpha. only if you look electromagnetic corrections. But unfortunately, you end up with all these loops with contributions of all possible fermions inside. So that means immediately that you can get quark contributions in diagrams like that. That means that something is going on what you don't like very much. That means that you have hadronic uncertainties even in G-2, what on first eye look very, very nice. And people are fighting with this source of uncertainty for years. And what's nice, lattice QCD also succeeded to consider this contribution light by light study in this year. It is its third published result. So you see this discrepancy is almost 4 sigma away, and it's very important to understand what's going on, and hopefully Fermilab first and then JPark later on might help us in clarifying this discrepancy. So let me come what you saw already today, and I thank previous speakers for mentioning that. So B physics anomalies are related to the ratio of branching ratios for decay of B to pseudoscalar or vector meson, to tau and nu tau, and also if it's normalized to the muonic, or actually in this case to all leptons. So basically that's in standard model, that's this diagram. And since 2012, it's almost 6 years, we accumulated such a data. And basically we got also standard model predictions, and heavy flavor averaging group in this year gave new averaging. And from 2012, there are some improvements in estimating the standard model, in calculating standard model contribution. But what's nice, we have also in last year from LHCb measurement of the similar process for B sub C to J psi. That means that only spectator quark, which will come here, would be C quark. And trend is the same. So we are kind of getting more data for the semi-leptonic decays with tau leptons in the final state. Another anomaly is related to decays of B meson to K star and muonic pair. And what happens, we don't have so many experimental results as in previous case, but it's after all, and summing all of that, we get pretty good evidence that there is a discrepancy of the order 2.1 or 2.4 sigma for RK, and for RK is 2.6 sigma. That's RK star. Also, it was mentioned and very nicely described that P5 prime is also one observable in angular distribution function, and there is a 3 sigma discrepancy. And very nice results is confrontation of angular correlations between muons and electrons, that one can really guess that maybe something goes wrong with the muons. Also see Capriotti talk at this conference. What's important, we also observe a discrepancy in B sub S to phi mu decays, lambda B to lambda decays. So it's almost many decays showing this anomalous behavior. As I mentioned already, when one thinks of standard model, because we know in standard model what's happening on the quark level, but when you have to put quarks inside the hadron, then you get a headache. So for example, for B to D, only vector current contributes, one has 2 form factors. And complete information on form factors comes from a Fermilab lattice and Milk collaboration. And we are very happy that we can get this information. So basically, we are quite confident in this result on the standard model value for RD. When it comes to RD star, what's known? Here in this decay mode, there are 4 form factors entering. 1 is from vector current, and there are 3 from axial current. And what's interesting in comparison with the pseudoscalar decay mode, that in this case there is a scalar form factor A0, which is not so important as F0 in the case of B to D. And we really don't have any input from A0 from any experimental data, as one can guess from B to D mu nu study of Q-squared distributions of the differential branching ratio. So far, we used two approaches. One is from Caprini, Neubert, and Lelouch from '97, based on heavy quark effective theory, and a little bit older approach of Boyd, Greenstein, and Lebel. And it turned out that the second parameterization is better in explaining VCB exclusive difference in previous year. So in order to understand what's going on these decay modes, we really do need lattice QCD form factors to settle this issue. Well, let me make one comment here. Before Fermilab lattice and Milk collaborations gave the result, again, heavy quark effective theory was used. But it turned out that this result is quite agrees with the prediction of Caprini, Neubert, and Lelouch from heavy quark effective theory. So that's also interesting. We don't expect that it's a huge discrepancy, but to be sure what's going on in the standard model, we really do need this. So what's next? If we are so confident that standard model works, we control it. So far, so good. Then if we cannot explain with anything within standard model observed discrepancy, we have to consider some new physics. What do we do then? The simplest way is like in old days when we searched for form of weak interaction, when we had a V minus A interaction, but we use it today not thinking a lot about it. In former days, in 50s, people were fitting all possible beta decays to get V minus A form. And now, since we are seeing better, having higher precision, we again do more or less the same thing. And basically, we can construct just extension of the standard model through this coupling GVL. Then we can allow variations for the quark current to have a right-handed component. We can add scalar contribution, and we can add also this tensorial contribution. And let me just say, if we believe that at low energy standard model is a good theory, then all these effective Lagrangian should exhibit symmetries of the standard model. That means we don't consider right-handed neutrino, but these people, at least 400 of papers, but I couldn't put it, consider many things here. But these people consider also effective Lagrangian with right-handed neutrinos, not only them, but that's a quite recent paper. What many authors favor is that's a fit value, that this vectorial coupling, modification of this vector current and vector current, V minus A currents, give us such an enhancement. So that means it's about 10% enhancement in the amplitude of the standard model. Let us assume following. Suppose we have some scale of new physics, lambda new physics, and that means these parameters can be replaced by such a coupling, and one can estimate that the scale of new physics in this case should be 3 TeV. That means that you put basically 2 is just that you handle a W charge current, don't worry about it, that this coefficient is basically 1 or 2. So that means that if you write Lagrangian in this form, instead of this GV, as I had it on previous transparencies, you get that that's a V minus A form of new physics, and it should be in such a form. We have to understand what's the origin of this factor here. But what's interesting, we can immediately study and understand that for a scale which is larger than 3 TeV, we enter into the problem of this CD altogether can become non-perturbative. And then that's something what we really don't like very much. So that means that we are quite limited with the scale of new physics. But in addition to this V minus A structure, people consider also another possibilities. For example, instead of V minus A, maybe 10 days ago, it was a paper of this group. Also, we use this formula. If one makes fit to RD, one can get also that modification of the scalar operator and tensor operator can explain both RD and RD star. As you see, standard model is here. And also, there is a quite dangerous contribution in B sub C to tau nu. So if one puts constraint that this new physics is not larger than 30%, one constrains this scalar contribution. So we can really survive with such a fit. And having fit to all other flavor variables, you will see that's a very interesting approach. Even more, what has been noticed by Ferrullo and collaborators, that this tensorial contribution can modify G minus 2, but condition is that you have both chiralities of top quark. That means that you have a coupling of mu to top quark effectively here with a tensor Lorentz structure. Also, you should have a hierarchical structure for tau, mu, and E in such a form that you realize possibility to explain G minus 2 by such a contribution. That's very interesting result, I would say. Let me discuss another anomaly. In B to S, mu plus, mu minus in standard model, we know that there are these box contribution and these two penguin contribution. Effectively, we get these operators, and what has been calculated a couple of years ago at the scale of the B quark mass, these Wilson coefficients are this size. So that's well established result, and I'm not going to discuss it now. So when we got all these experimental results, a lot of excitement, people looked what can happen and what can fit this result, and assuming that new physics is in muon sector only, it is by many authors that almost best fit what one can do is that new physics show up in the operator of vector coupling for muons and axial vector for muons, and you really need such a modification of the standard model to get an explanation of new physics. Putting again question, what is the scale of new physics? That means writing the Lagrangian in this form. One gets, here scales can be quite large. And many people modified their calculations according to this. And what did we learn out of this? First of all, if we see that RD star is larger than experimental value than standard model value, for RK star, it's just the opposite. Here you need 3 TV scale, here you need 30 TV scale. So if we are very ambitious and try to explain with the same new physics both B anomalies, then in this case, one should get that obviously contributions in the kaons should be suppressed by a factor of 10 to minus 2 in comparison with the new physics in charge current. So that's something what we know. How this suppression is achieved? This is one of the most favorite scenario right now, that you try to explain both anomalies through these two effective Lagrangians, but don't think that there are only these two couplings. There are some other couplings hidden within this node. But what happens if you assume new physics in muon sector, and if you try to explain RD star with the standard model, you get for certain choice of parameters, you get that it's possible to do that. People also notice that such a Lagrangian implies that there is immediately lepton flavor violation. So that if you try to explain these B anomalies, you get extra contributions from lepton flavor violation. Well, what are the possibilities to explain it? Many favorite scenarios are related to Z prime, and that basically this coupling is small altogether, that it should be 10 to minus 2 in comparison with the charge current. And there are scenarios, what I mentioned here. If you want to make a UV complete theory, then you need some vector-like fermions, even vector-like leptons, and many things can be done with this. Another possibility is to realize that new physics is at the loop level, as has been suggested by Bauer and Neubert, but then due to all constraints, it turns out that it's not that easy. So suppression factor here really comes from the loop. And when you start doing this, your favorite literature should be particle data booklet. What happens many people when we are doing this, you have all these flavor observables, I hope I didn't miss some, and you have also constraints from lepton flavor violating processes. And when you make your Lagrangian effective or model Lagrangian, you should look all of them to see if something is happening, if something is constraining your new physics. For example, here you have these two simple examples, what's happening. So where are we now? We have low energy flavor constraints, we have new physics effective Lagrangian, but we are ambitious. We want to build some complete theory of new physics. In order to do that, one needs LHC flavor constraints. But if you do all these things, just keep in mind what Feynman said. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. So here there are plenty of models built to explain both anomalies. There are leptoquarks and pseudo-Nambu-Goldstone bosons, composite leptoquarks, vector resonances from technifermions, models with scalar leptoquarks, gauge bosons. Even in extra dimensions, people tried if that can be explained. So leptoquarks are the favorite choice of anomalies. Leptoquarks are objects which can couple lepton and quarks, and they can have a spin 0 and spin 1. And they can have such a quantum numbers of SU3 QCD, of SU2, and this is hypercharged normalized in this way. So you can see here quantum numbers, and this table tells you which leptoquark can explain RD, which can explain RK star, and which can explain both. So you end up, if you have only one, that's this vector leptoquark, which is a singlet of SU2. Let me just comment here that R2 and S1 might explain G minus 2 because there are both chiralities in principle. So if you keep in mind that there is this anomaly, one has to know that. So group from Zurich succeeded to analyze only one leptoquark mediators, and they really got that U1 is best candidate, that it can explain that can satisfy all constraints and explain both anomalies. So that's very good candidate, but they also tried to make full theory, and they found out that this leptoquark can be put in a Gatti grand unified theory of Patti-Salam type. That means that leptons and color of quarks are put in SU4 group in one representation. But in order to satisfy, to get a proper flavor structure, they really ended up with a Patti-Salam model onto the third potential, they call it three-site model, which has nice features, that it has many new gauge bosons. It might be that some signal will be seen at LHC. Unification is rather low and no proton decays, but it's really good. And also it can solve a flavor puzzle. Two leptoquark solution of RD and RK, that's another possibility, two scalar leptoquark solution. So why to have two? It's possible to make GATT theory with two light scalar leptoquarks. There is proton decay can be avoided, and neutrino masses even can be generated. People tried combinations of SU2 triplet and SU2 singlet. This is really very good for B2K nu bar constraints. And that works, but there is a problem with the Z2 lepton pair production, radiative corrections. So what we tried to do is we took this leptoquark R2 which can create scalar and tensor contribution to RD star, what you saw that it's a good solution. Basically, that's new physics of this type. And what we got is that we really fit to RD, and RD star pushes us to get imaginary coupling, which is slower than 1. That's a good feature. If it comes to RK, this is the basic diagram. Second leptoquark, what we call the S3, which has a charge 4/3, can explain it. But we end up with a model which is having only 4 parameters. One of them is complex, and that means 3 parameters and 1 angle, and masses of R2 and S3. Very important is that these 2 leptoquarks are in the same gut representation, and the nicest feature is that we got couplings which are smaller than 1. Here are predictions for lepton flavor violating process, and here is already a Bell bound for R nu, which is the ratio of these 2 decay modes. So, as I said, one should look also for LHC constraints of new physics, and this is particularly this signal of 2 tau plus tau minus, and you see that for vector leptoquarks, you're already reaching the exclusion limit almost. And also one can look for the muon pair for leptoquarks in B puzzle. That's for this diagram. But for RK star, when you have PP to mu plus mu minus, then you see that that's the region for RK star. And you see that some models with the Z prime are already having troubles with this constraint. And let me just explain this figure. This is explanation for 2 leptoquark pairs. This line gives you all low energy flavor constraints fit to them for these 2 couplings presented here. But this black line here, it comes from perturbativity of all these couplings up to gut scale. So you cannot go farther than 1 if you want to have perturbative coupling up to gut scale. But then you go to see what Atlas and CMS were doing, and then you get a constraint from BB bar, CC, and TT bar. But also CMS has exclusion region for leptoquark pair productions, and if we put their results, we end up really with only this white region allowed by LHC, and yellow region inside is allowed by low energy phenomenology. And you really live in such a small parameter space. So what we can ask next, and I will finish my talk now because I'm running out of my time, and also look what are the consequences for K2 nu if new physics is present, and I will just summarize. If you look from RD star as it's done by these people, then new physics in K2 pi nu is suppressed by 30, standard model is suppressed by 30%. And if you have new physics from RK, then you get a maximal enhancement of 50% and 10% in K0 long to pi 0 nu bar. And let me give you a final goal is to understand the masses of all leptoquarks, and that can be even done using B meson anomalies. I cannot explain you anything more because I'm out of time. And let me just give you outlook. What do we need? If we have to wait first on Bell 2 and LHCb new results to get to be sure that there really is something new going on. We need this lattice result for B to D star form factors and also for these decay modes. Experimentalists are urged to measure all angular correlations possible for B to D star tau nu, and also test all possible observables for B to C, B to S mu mu. Then what else? If we have new physics in RD and star and RK star, then there is no way that these processes are not affected. So we really do need as precise as possible. Some of them is not possible to measure, but we need as precise as possible bounds on these processes. So we also should wait on tests on flavor couplings at LHC. we also shouldn't forget first and second generation and to look for tests of lepton flavor universality, and being happy with all of that, we eventually end up building effective Lagrangian as well as new physics models in the future. So I would like to thank you, and keep in mind, I like this saying, so I would rather have a question that cannot be answered than answers that cannot be questions. So thank you for your attention.
Thank you. Is there any question?
So on page 16, you were showing very nicely that you had all these various constraints you have to respect. And one of the lab legacies was per mil level universality tests in tau, mu, and e decay. I mean, tau and mu decays, and looking also at the tau lifetime. And I'm wondering, so this tree level RD star is a very large effect. Is this really, so can you really build models which then would not even give a per mil contribution to tau decays?
You mean for tau to mu gamma and tau to phi mu?
No, tau to mu e, tau to e, tau to mu, neutrinos, and tau to e. So the universality test tau decays, which is really, I mean, it's a few per mil.
Look, what I know from these models, usually RD star pushes you to have large couplings. That's problem basically with many models. If you have relatively small couplings of new physics, as I showed you, of the order 1, then you are not in such a danger. But I know DD bar mixing is terribly constraining for many models. Also, D sub S and tau or neutrino, mu neutrino, they are really extremely useful in constraining all this physics. So I cannot tell you in particular model, you should look all fit what's happening, but one should look all of them.
Actually, I just want to make a historical remark. Since we're discussing the breaking of lepton universality, probably one should recall that the idea of lepton universality of weak interactions was launched by Pontecorvo in 1947.
Thank you, Sergei. Yeah, but I should add also in 1957, it was the first idea to measure G-2 by Garvin and Lederman group. So it's historically, it has development.
Okay, so we thanks again all the speakers.
Thank you.